come back to our class. So basically for the last hour, I guess after we have been talking so much about polynomial time reduction, and basically we have been introducing the basic strategies about simple equivalence, about like special case to general case, and also gadgets. We are probably going to give like a little bit more formal definition about like complexity classes. So this is basically going to be the next step that we are going to do here. Okay, so we need to give the definition of some common complexity classes. Oh, excuse me. So I need to give the definition of some common complexity classes. So I'm going to give the definition of P and NP. So those are probably, very famous terms that we probably need to give a little bit more, formal definitions here. So basically, we say that in general, basically for the end of last lecture, we talked about self-reducibility. So we say that actually we can formulate a decision problem as follows. So basically, we know that in general, we can without loss of generality say that the X, the input is basically a set of strings. And an instance that we study is basically a string S. And basically, we say that an algorithm A solves the problem S. We say an algorithm A solves the problem X. That is the case where the input, if it's S, AS give you an answer yes, if and only if S belongs to the set of S here. So basically, we just characterize each problem as a set of strings, and basically for a string S, to input to encode some instance of a problem. We say that the algorithm solves the problem X, and basically gives the value AS equals to S, AS equals to yes, if and only if S belongs to X here. So this is basically we just like turn the problem into this kind of representation. So basically do a representation that whether each binary string is inside the problem X or not to determine whether the algorithm will give you actually an answer yes or no here. So this is basically a very formal definition that we are actually going to give about like what is so-called a polynomial time. So for polynomial time algorithm, basically we say so if for every string S, algorithm are running AS actually terminates in at most P of S steps. Where P is a polynomial and S is the length of S. So basically, this is polynomial time. This is very intuitive, I guess. It's just saying that a correct algorithm that actually runs in polynomial at most a polynomial number of steps. So basically, the complexity class P is just decision problems for which there is a polynomial time. So. Okay, so this is the definition of the complexity class. So P is, I guess, is relatively straightforward, but we probably need to define what is NP. So NP is a little bit more sophisticated. So we probably need to give a little bit more discussion about that. So now we go to NP. So actually, the complexity class, it is actually NP here is actually potentially broader than P here. just need to make the English correct here. And basically, we talk about quite a few different problems. We talk about the three-set problem, independent set, where vertex cover, set cover, three-color problems. As far as people know, none of these problems have a polynomial time algorithm. As far as people know, so people have been wondering about, whether these problems is a polynomial time algorithm or not. So people are not sure about this, but in terms of complexity theory, we can have like a formal definition that hopefully a certain complexity class can actually contain all of these problems, and maybe at least we can have a good understanding about these problems. So basically, this NP is actually proposed in this kind of perspective that hopefully it's like a complexity class that is actually broader than P here, and actually contain common problems that we study. Basically, such as those we discussed. So basically, these problems, as I just mentioned, as far as people know, none of them people know polynomial time algorithm. But we still need to have some kind of sense that we characterize, these problems are not super complicated. Like the problem in P, they are nice in the sense that they can be solved in polynomial time. Here, we also need to get some intuition along that. So basically, we say that how are those problems simple? And actually, we need to have a better understanding for that. So the key thing is that, along the reduction that we have been talking about this. So typically, you can probably see notice something that, for instance, maybe talk about this reduction. So for this problem, for the reduction from three set to three color. So basically, we talk about like the equivalence here that maybe somehow you magically give me a certain answer to like to say like a three-color problem, then basically, we can have a good understanding about like what is the corresponding satisfiable solution for the three-set problem. So in some kind of sense, in all these kind of reductions, somehow it is more like we are assuming some kind of certificate. So basically, this certificate is really a very important definition. So formally speaking, we say that this is called like a certifiable. Certifiable. So basically, although for a lot of problems, so basically giving a solution is difficult. But actually, verifying the correctness of a solution is simple. So that is to say, actually, a certifier doesn't determine that whether actually S is in X on its own. This is the main point where actually NP is different from P. For P, it's just like, you give me an input and I tell you whether this is actually in the decision version of a problem, whether this is a yes or no here. But actually, a certifier here not only takes, does not like actually determine whether S belongs to X or not on its own. Actually, we have something extra. So rather, I would say is that actually, it actually checks a post T actually S belongs to X or not. So basically, it has some kind of extra assumption that basically we can efficiently certify the correctness of a certain problem. That basically, for the problem in NP, that is basically saying that we have kind of like a certification for that. So we actually can make this a little bit more formal here. So like a definition. Here is that we say that an algorithm CST is a certifier. For problem X. So if for every string S, or S belongs to X, if and only if there exists a string T. So basically for such kind of string T here, so we just typically call this as a certificate, or we call this as a witness. A string T such that CST equals to yes. So basically, this is the point of having a proof that basically there exists a string T that can be used as a proof such that the value of CST equals to yes. And in a no case, I mean, no matter how you give a proof, I just know that this is just wrong. So this certificate is just the most important thing in terms of the definition of NP here. So now we can formally define what is an NP problem. So basically, NP characterizes decision problems for which there exists a polynomial-time certifier. So actually, it means that CST is a polynomial-time algorithm. And actually, the length of the proof, basically the T here, is at most P of S, or some polynomial P. So this is the definition of NP here. I guess I probably need to make a remark. I mean, if you call a problem to be in a P here, just polynomial time, this is very straightforward. But here I'm talking about a complex class of NP. So what is N here? So we need to mention that the NP here stands for non-deterministic polynomial time. Deterministic polynomial time. The P here is the same as the P in the definition of complexity class P here. But here, the first word, non-deterministic, this is leading with N here, and why this complexity class is actually called NP here. So the reason saying that why actually this is called like a non-deterministic polynomial time. So this is basically the intuition is that actually searching over the space of possible proofs can be viewed as a non-deterministic search. Okay, so I mean, in general, I mean, for the T here, so the T here is actually a string of polynomial length. But if you don't have any idea, I mean, in general, just like try this brute forcely. I mean, there are just exponential number of choices. But actually, you know its existence. You just I mean, in the yes case, you know its existence. You just don't know what it is. So this is basically, I mean, if you give that to me, I can actually verify the correctness of the proof here. So this is actually a formal, there's an intuition that actually we have been talking about all the way here. And actually this is a way that we can actually formally write down the definition of the NP complexity class. And actually this is called a non-deterministic polynomial time. And definitely, I mean, for a lot of beginners in complexity theory, people thinking about NP represents not polynomial, but this is definitely not true. It's very difficult to actually prove that there does not exist a polynomial time algorithm for a certain problem. But actually, I mean, in general, the NP here just represents non-deterministic polynomial time. Okay, so is there any definition about a question about the definition of complex class P and NP here? Okay, so let's probably still move around using some examples. So I guess we talked about, I mean, basically for the problems like the three set, basically like three colorable and independent set, vertex cover, etc. For these kind of problems, we say that probably there are actually problems in NP that in general we want to characterize this. So we probably need to make this a little bit more explicit. So let's say example. I mean, basically we show that the set problem. I mean, the three set problem is like a special case of set. So let's just say that the set problem is actually in NP. So how do we actually do this? So an instance is probably something that we just talked about. Maybe for instance, it's like x1 with x union x2 union x3 and x1 union x2 bar union x3. So let's maybe for instance just write down like a three set here, but it's actually nevertheless a set problem. So it's basically, I mean, this is just an input instance. So I guess we have been using the letter S. So this is an instance S that we actually want to study here. So actually we also have like a certificate key here. So actually we know that this is a yes instance for the set problem. And actually it is not very hard to check that actually we can just input a string which is like 1101, like greater than x1 equals to 1, x2 equals to 1, x3 equals to 0, and x4 equals to 1. I mean, I just tell you this certificate. You can just check, actually, this is a satisfiable assignment for the corresponding clause here. But if this is a no instance, no matter what you give me, I just noticed that it's not satisfiable. So this is actually the point of the NP here, that as long as actually you have like a yes answer to the problem, you should be able to find a certificate. But if the answer is no, I mean, if it is not a satisfiable assignment, no matter what you give me, I will always reject them. Okay, so this is like for the set problem, and also actually for the set cover problem. For the set cover problem is actually also in NP. So the instance S is actually something like U maybe equals to 1, 2, 3, 4, 5, 6, 7 here, and we have a bunch of different sets. So let's actually just feel free to copy that, I guess. Let me actually find the place where we talked about that. So let's actually talk about this. And let's copy it here. So for this problem, I mean, we know that, I mean, actually for k equal, and also very importantly, we need to have the assumption that k equals to 2 here. But nevertheless, for the certificate T here, you can just give two values which are 2 and 4 here. Actually, x2 x4 is actually a certificate for the problem. So actually, I mean, what I'm saying here is probably quite trivial here, but you can just imagine that actually for the problems that we have been talking about, there are actually a relatively very standard problems in NP, and you can very easily find like a certificate for such kind of problems. So maybe like a remark I'm actually going to make here is that you will find very common in complexity theory that here, actually we have the assumption that the X here is actually composed of binary strings. Basically, we also assume that the input instance is also a binary string here. So maybe there is a question that, okay, here, for instance, like set cover, we talk about like integers and basically like sets here. And basically for the set problem, I mean, okay, this is Boolean, but we also have like clauses here. So basically we need to be careful about, I mean, how you actually store the binary strings. But actually, this is not something people really care about by much. As long as we know what is like a problem and we know what is the structure that we are actually saving the problem, it is typically fine. So a quick remark here is that basically for the problems we study, we actually can encode them into binary strings. And instances of size n have polynomial bits. Okay, so let's see a few examples here. So for instance, for the first set, so say if we have n variables, so actually we know there are at most, then choose 3, which is actually O and Q classes. So basically, each class actually can be stored, let's say by 3 of log 2n plus 3 bits. So basically, we can use like log 2n bit for literal, like 1 bit for overhead heavy negation. So that is saying the overall length of S O of n cube log n is actually a polynomial in terms of n here. And actually, in our in the 3-set problem, basically T has length n. It's basically like the ith bit string, last bit of storing. Actually, on xi equals to 0. And basically this finishes the argument. So basically for the problem that we have been talking about, I mean, for like 3-set, independent set, vertex cover, set cover, etc. I mean, you can clearly see that in general, it's not very difficult to find a binary encoding for the problem. It's basically, I mean, that is a main reason that for our convenience, when we talk about, I mean, P, NP, these kind of problems, we always talk about like a binary complexity classes. I mean, this is probably a little bit easier to make everything more clear. But in general, I mean, to reduce like a whatever problem to like a binary encoding, encode as like a binary representation is relatively standard for the problems that we study in this lecture. So this is typically not the part that we are really worried about in general. Okay, so I mean, like a remark here, as we just mentioned, is that as we are, so basically, as we are talking about polytime reductions, excuse me, polytime, we don't worry much about how the encoding is given. So as long as it's polynomial, we are good. Okay. So let's actually give a quick recap here about like the complexity classes that we actually are studying here. So we have been talking about the complexity class P here. So, and actually also the complexity class NP here. So let me also actually include another complexity class called EXP here. So these just represents like decision problems for which there is. I'm actually just too lazy. Let me actually just copy this. Here. But what is going to write next is different. So P is actually just decision problem for which there is a polytime algorithm. Polynomial-time algorithm. And actually for problems in NP is that basically a decision problem for which there is a polynomial-time certified. And next class for exponential or complexity class is basically for decision problem for which there is an exponential time algorithm. Okay. So here, I guess there is a little bit mismatch because for NP, we are talking about polynomial time certifier. NP and exponential EXP is basically very standard complexity class talking about like the time complexity of algorithms. So we probably need to have a good understanding about like what is a corresponding relationship. So like first a theorem is P is a subset of NP. So I guess this is a very straightforward proof. It's just like take T to be empty string for a problem X in P with algorithm A. I mean, as long as we have a problem in P, I mean, it has a polynomial time algorithm. We can just create a certifier where the proof is empty. I mean, this algorithm just solves the problem. So of course, P is actually a subset of NP here. I guess this is, should say this is probably. But actually, on the other hand, we probably also need to understand what is like the limit of NP here. So if having like a polytime certifier is just going to be super powerful, that is also not something we want. So another theorem that we actually can establish is that actually NP is a subset of exponential. So let's actually prove this. So the proof is actually based on the fact that we use the polynomial time certifier here. So the length of T here is still at most a polynomial in terms of the input size S here. So let's do this. So let's actually consider any problem XE and P. So by definition, there is a polytime certifier. Certifier CST for X. So actually, to solve input S. So one thing that we can do is that maybe we know that actually we have like a polynomial time certifier here, but I mean, in general, I mean, if we don't have like the proof here, we don't know what it is. But at least we know that it actually has like a polynomial time, has polynomial length. So actually, I mean, if we want to consider like a very brute force way of doing the algorithm, I mean, to solve input S, we just run CST on all strings T with the length that T is actually smaller than P of S. And actually I'll return yes. If CST returns yes for any of those. And actually, I mean, the 2 to the, because the length of T here is at most polynomial. The total number of trials here is basically 2 to the P of S, but this is still exponential. So actually we are fine that in general, I mean, if you're okay with just brute forcefully check everything, I mean, of course, any problem in NP here is going to be in exponential time. This is, for instance, let's think about the set problem. So for the set problem, I mean, in general, we have all these kind of clauses, and we have like say n variables from x1 to xn. I mean, a brute force way is just like you check like x1 until xn, all 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, etc. You just try all the possible 2 to the n choices. You will know that actually, if one of them is actually giving you a yes answer, you solve the problem. And actually, if all of them give you the no answer, you just auto no. So in any case, we know that actually NP is a subset of exponential time. Okay, so is there any question for the theorem that P is a subset of NP and actually NP is a subset of exponential? Okay, so as a quick remark, I mean, for this theorem that actually NP is a subset of exponential time, I mean, the intuition is actually quite clear. So it's just like a brute force checking. So we say that intuitively this proof is actually checking all the possible 35 errors. Which takes exponential time. Okay, so here we have like two relationships that P is actually a subset of NP and actually NP is a subset of exponential time. So actually in complexity theory, people know that P is actually a proper subset of exponential time, that there actually some really contrived problem that you just cannot solve in polynomial time, but can be solved in exponential time. So there is such kind of result. But actually the relationship between like P and NP and NP and exponential is actually people just don't know what is the specific relation. So like a very main question here that people ask is actually does P equals to NP? So actually, this is one of the, I should say this is probably one of the biggest open problem in computer science in general. I mean, if you can solve that, I mean, you can, I mean, win $1 million, at least win $1 million. I mean, this is because based on the clay price. So, I mean, answering this question will be just marvelous and actually have a lot of implication. Because I guess in general, the situation is that for the problems like the three set, three color, vertex color, independent set, etc., for all of those problems, people, I mean, people have been really trying this for decades and decades, and no people can find a polynomial time algorithm for any of them. But people, on the other hand, can also not prove any like lower bound that basically none of these problems in polynomial time. So this is really like a dilemma here. I mean, in general, I mean, people have been really thinking about this problem, like whether P equals to NP. Have you think about this for a really long time? I guess people are probably still very far from solving that. But in general, maybe let's say about talk about some implication on this. So if the answer to this question is yes, so that is basically saying that we are going to have efficient algorithm for a huge amount of problems. So we are going to give efficient algorithm for like say the set problem, and also like the factor problem, like the problem where we want to factorize large integers. And actually the TSP, the traveling salesman problem, that you have a graph and you want to find, I mean, if you want to visit all the vertices and you want to find the shortest path, the traveling salesman problem, etc. But if the answer is no, if the answer is no here, that is basically saying no efficient algorithm. Is actually possible for set factor traveling salesman problem, etc. I mean, although this is like this is still a conjecture. I mean, whether P equals to NP or not, people have some consensus. So there are some consensus opinion. On P equals to NP. So like in general, people feel that the answer is probably no. But if we really want to prove this, I mean that P not equals to NP, I mean this really needs some fundamental change in terms of complexity theory, and people just have no answer about how this is actually going to work. Okay, so this is basically about like P, the problem of P versus NP. So here, I think I also want to introduce something a little bit different. So compared to NP here. So for the problem of NP, so here I think we have been talking about, I mean, whether, I mean, for a specific problem, I mean, whether there is this, if there is a proof to prove that there is actually an answer, and basically we're going to have yes. And actually, if for all of the proof this is not going to work, actually we are going to say no here. So somehow this is like an asymmetry here. So asymmetry here is actually a little bit bothering. So actually for the NP, actually we only need to have short proof for yes instances. So for instance, I mean, like the set problem, I mean, if it's a yes instance, we just like, I mean, it's the T here is just like a binary string of length n here, then you just know actually it has like a satisfiable solution here. So here, like a question, I mean, for the set problem, maybe you can also ask a question is that how could we prove that a formula is not satisfiable? I mean, or in general, I mean, for a lot of problems, maybe we actually want to consider a case where actually maybe like proving the we actually want to have short proof, maybe not for yes instances, but actually for no instances. So this is actually also quite a common consideration here. So actually a corresponding definition that we can consider. So it's that basically given a decision problem. So basically it's complement X bar is the same problem with the yes and no answers reverse. Okay, so let's see, for example, so we can talk about the prime problem. So for the prime problem, we have a set of strings, and that is actually a 2, 3, 5, 7, 11, etc. The set of all prime numbers. So if we consider such kind of complement, we will actually get a set of composite. I mean, we can just feel free to actually maybe put 1 inside the set here. I mean, this really does not bother us. So we can put the 1 here, but actually otherwise, I mean, this other value like a 4, 6, 8, 9 here, etc., which is going to be the set of composite integers other than 1 here. So we clearly see that probably, I mean, consider like a complement of a problem is going to be something non-trivial, I mean, in general. So this actually comes to the definition of the complexity class of co-NP. So this co here just represents complement. So it's actually complements of decision problems in NP. So this is actually another very important definition in complexity theory. And I mean, also another important point. I mean, actually, you can show that for the P problem, for the complex class P, actually co-P equals to P here because you have an algorithm. I mean, it's not about issue with a certifier. You just run an algorithm. I mean, if it's yes, it's just like return yes. I mean, if the answer is no, it's just return no here. So it's clearly see that co-P equals to P here. But for NP here, I mean, if you want to talk about a certifier, I mean, you're talking about whether you want to have a short proof for the yes instance or for the no instance. This is definitely going to be something different. So in particular, I mean, we can probably see the intuition here. So intuitively, so for a problem X in NP, so for yes instance, there is a succinct. I mean, we have been talking about this for a long time. So it is going to be for succinct certificate. But on the other hand, for a problem X in co-NP, so basically for no instance, there is a succinct disqualifier to actually give a short proof for the no instance. So this definition of co-NP is actually also a very important in general, and I guess maybe having, as I just mentioned, like co-P equals to P. So here maybe we want to ask the fundamental question, another fundamental question. I mean, at the similar fundamental level to the question of whether P equals to NP, is that whether co-NP equals to NP. So the consensus opinion is still probably no. But why is this the case? So a key point is that actually the theorem is actually this is an even harder problem than a P versus NP problem. Because if we know that NP not equals to co-NP, then P not equals to NP. So we can actually give a proof for that. The proof is actually quite simple. I mean, we can do something like this. So as we just mentioned, P is clearly closed under complementation. And on the other hand, actually, if P equals to NP, then if P equals to NP, then we know that NP is closed under complementation. And this is going to imply NP equals to co-NP introduction. Okay, so if NP not equals to co-NP, we know that P not equals to NP. But actually, on the other hand, proving NP equals to co-NP is actually also sounds like some super complicated problem that people, at least as far as people know, I guess we are still very far from showing that actually NP equals to NP or NP not equals to NP. This is really something essential that people don't know actually how to resolve. Okay, nevertheless, we can still make some further observation here. Like one of the further observation is that actually we know that P is a subset of the intersection between NP and NP. Actually, the co-NP should be. So that is because actually P is a subset of NP here, and actually co-P is a subset of co-NP, but actually co-P equals to P. So we know that P is actually a subset of NP intersected with co-NP. I mean, we can also ask the fundamental question. I guess basically I kind of feel that for the first 2 hours of today's lecture is more about like algorithmic part, and basically for the last hour is basically about complexity theory. But for complexity theory, we got to give some definitions and some basic arguments. So I guess I probably just need to introduce this. So fundamental question is actually asking does to NP intersect with co-NP? So for this question, people have really mixed feelings. So people really don't know where actually, I mean, whether P equals to NP intersect with co-NP. So here, let's actually take a closer look at the intersection between NP and co-NP. So let's consider a specific problem here. So let's consider a problem of the factor. So for the factor problem, we ask this. So basically given two positive integers, x and y, does x have a non-trivial factor smaller or equal to 1? So this factor problem is actually a problem that is actually in NP and co-NP, intersected with co-NP. So theorem. So why is this the case? So I guess this intuition here is actually quite straightforward, that basically for problem in NP, it suffices that we have like a succinct certificate. And for problem in co-NP, it suffices the problem has a succinct disqualifier. So it suffices that for us, if we want to show a problem is in NP and co-NP, we only need to show that problem is the factor is in NP and factor is in co-NP. And actually it suffices that we mention what is the certificate and what is the disqualifier here. So for a certificate, I mean, like a succinct proof that actually we have a yes instance. I mean, if it is a yes instance, I mean, a succinct proof is just like a factor P of X that actually smaller than. I mean, of course, this is going to be a certificate that actually to guarantee, I mean, if you can give me such a proof, and actually we know that this is, I mean, because like actually, I mean, have a large number and you divide by a certain number P here. I mean, this is just trivial. You can just do this in, very efficiently. I mean, after you give me a proof, I mean, we can, it is very easy that we can verify this. So this is a certificate. And actually for this problem, we also have very good disqualifier. So a disqualifier is just like a prime factorization of X. Where each prime factor is larger than Y. I mean, as a disqualifier, it suffices that you give me a prime factorization, and okay, I look at that. Each of the prime factor is actually larger than Y. And actually, another very important note is that actually determining actually whether a number is in prime is actually whether a number is prime is actually in P. So basically this prime problem can be solved in polynomial time. So this is actually another well-known result that I think probably one of the most important algorithmic results in the past like 20 years. So basically we know that prime is actually in P here. So actually, as a disqualifier suffices that you give me a prime factorization of X, and where each prime factor is actually larger than Y here. And the suffices that you check, okay, each of them is indeed a prime number, and actually, okay, multiplying them together gives you the X, and okay, all of them are actually larger than Y here. So a very important thing is that for a prime factorization, that actually X here equals to some P1, P2, until whatever. So if it's like a prime factorization for arbitrary I, and for arbitrary I, Pi is actually larger than 2. So this is just saying that the length of prime factorization is actually at most log 2x. So if I give you this kind of prime factorization, the number of prime factors should only be at most log 2x. So this is very efficient in general, and this is actually a very good disqualifier to show the problem. So basically, we clearly know that this is actually a short proof that actually the factor problem actually in NP intersected with co-NP. But actually, on the other hand, currently it is not known whether a factor is actually in P or not. Okay, so basically, I mean, I have one last minute or two. So basically, I think the last definition that we are going to give is called NP completeness. So we say a problem Y NP complete if actually Y is in NP and for any X in NP, X can be reduced to Y in polynomial time. So this is the definition of NP complete. So intuitively, you can imagine that, okay, this sounds like the hardest problem in NP. So it is still in NP, but whatever, you give me like a whatever problem, I mean, X, you can just reduce this problem to the Y that you're actually I'm talking about. So this NP completeness is actually another very important concept that actually basically this is the most important concept that I'm actually going to introduce in the next class. So basically for the next class, we are basically going to establish NP completeness for many natural problems. Okay, so basically for the lecture today, I think basically I keep talking about polynomial time reductions, and I have been giving the definition of PNP, co-NP, and NP completeness. And basically for the next lecture, I'm going to talk more about NP completeness. And basically, I mean, because the title of this course is the algorithm analysis and complexity theory. I guess basically for complexity theory is basically for this lecture and next lecture. And let's go into the details of NP completeness and beyond. So for the next lecture. So thank you for your attendance today.